Hello, everyone, and welcome back now to chapter 6. And this is part 2, and this is a very, very small part where we'll just be talking about ATP. Because ATP is immensely important. It's a molecule that we call adenosine triphosphate, and it's basically some sort of nucleotide that we use in our body as energy. It's literally, we call it as the currency of energy that's used in cells. As we learned, exergonic reactions can happen spontaneously. You just need a bit of that activation energy just to spark it up a bit. But endergonic reactions, they cannot happen spontaneously. You need extra energy to for them to happen. And there's a lot of endergonic reactions happening in our cell. So you start thinking, where are they getting that extra energy? They get it from ATP. So let's take a look at ATP. So ATP has the following structure, very, very similar to basically a nucleotide, where you have a ribose ring, and in your carbon number one, you have an adenine nucleotide, and then here, basically, in your fifth carbon, you have three phosphate groups. So ATP is adenyl triphosphate, but it can also exist as ADP, meaning adenyl diphosphate, so hence it only has two phosphates, or AMP, adenyl monophosphate, so meaning it just has one phosphate. So these are very important because these kind of bonds between the phosphates and the oxygen are high energy bonds. These bonds contain so much energy, and this is basically where they're basically, if you break these guys, this is where you're going to give off energy to yourself for this endergonic reactions. So the thing about this ATP molecule is very unstable, and simply because you have this very high energy bonds, and then you have a lot of oxygen, these kind of negative charges on your oxygen. So you have it here, there, and there. These guys repel each other. They don't like each other. So they're always trying, repelling each other. And then you have these very high energy bonds. So basically, in some sort of way, you can see it as a small little spiral. So think about it as this kind of, let's show a good picture. Spiral bouncing. Kind of this is exactly what I was trying to say. It's kind of those kind of bouncing spiral. It's like it keeps, going back, it comes together and then it goes up and forth, back and forth. So these literally spring metals that are just bouncing up and forth. Well, that's basically this thing here. So this is why it's so stable. It's always in motion because you have the O negatives that are always, repelling each other, but then you have these energy bonds that are, trying to keep this back in place. So they're bouncing back and forth. So ATP technically is very unstable. So to use this ATP to store energy for long periods of time, not really. You cannot do that. If you want long-term energy storage, phosphate bonds are too unstable. So these phosphate bonds, fats, carbohydrates do it much better. So ATP is just used for like a few seconds. It's really quick and easy. You create them and they're really used there to basically be broken. And what happens here is that when you get ATP and you put water through hydrolysis, so remember where water splits and it breaks down basically macromolecules. So this is what it's doing. This H2O is literally breaking down this, and it breaks down this to ADP. So meaning that this is ATP triphosphate. It breaks this bond, this phospho-oxygen bond right here. It breaks it, and this energy that's in this bond is releasing. And that by itself is something around minus 7.3 kilocalories per mole. That's just the amount of energy. And this is enough to fuel all the endergonic reactions in the um, cell. And I'll give you an example. So sometimes you have glutamic acid and ammonia that combine together to give glutamine, which is another important amino acid that you really require in your body. However, this has a positive delta G. It has 3.4 kilocalories. Hence, it's very endergonic because it's positive. So this guy, the glutamine, has much more energy than glutamic acid and ammonia. So remember, delta G is actually measured by the G from here, basically from your products, minus the ones from your reactants, your reagents. So if we put ATP as we said has minus 7.3. So basically now, if we now sum this all up, you're gonna get minus 3.9. Because now this guy has much more energy. It has basically, let's say 7.3. Well, this one has 3.4. So if we apply basically the delta G, it's minus 3.9. Hence now we made it exergonic because ATP has given that phosphate. This phosphate, so ATP has been broken down. It's given phosphate here to the group, to this very high energy bond to it, which then can be basically, give a what it does. It gives the reagents much more energy. Hence, delta G will become negative. So that's how ATP can work, and it can be coupled with endergonic reactions to make them exergonic.